This is the Math 2 lesson summary video for B there or B square. In Lesson 5 of Unit 4, B there or B square, the purpose of this lesson is to connect the idea of completing the square to the vertex form of a parabola. We convert quadratic functions from standard form to vertex form and then graph the function. Some vocabulary that we need to be aware of is that the standard form of a quadratic function is when the quadratic function is in the form y equals ax squared plus bx plus c. The vertex form of a quadratic function is when the function is in the form y equals a times the quantity x minus h squared plus k, where the hk is the vertex of the parabola and the a is the vertical strength or stretch. Through this lesson, we will also use the vertex and the a value to help us graph the parabolas. In this lesson, we are told that Optima's niece Jenny works in the quilt shop, and when the shop isn't too busy, she takes out her math homework and works on it. One day, when the shop wasn't too busy, Jenny was working on graphing parabolas. The equation provided to her was y equals the quantity x minus 3 squared plus 4. She realized that this equation looked very similar to the quilt orders, but that the side length of a standard square was reduced by 3, and she had to add a little piece of fabric that had an area of 4. When asked to describe what this graph would look like in number 1, we used our prior knowledge regarding maximum and minimum values and the axis of symmetry. After graphing the function, we determined that the axis of symmetry was the line x equals 3. And it had a minimum value at the point 3, 4. We can tell the minimum value by examining a table of values for our function. If we look at a graph of this function, we can see that the minimum value is indeed 3, 4. And that the axis of symmetry would be the line x equals 3. If we examine a table of values, we notice that the y values are symmetric around the value 3, 4. For example, we can see that 5 and 5, 8 and 8, and 13 and 13 match up on each side. The reason this happens is because a parabola is symmetric along the axis of symmetry. Therefore, our x value for our axis of symmetry needs to be 3. If you recall also from Unit 3, we know this is going to be a parabola based on examining our y values in the table. The difference, to get from 4 to 5, we would add 1. To get from 5 to 8, we would add 3. To get to 8 to 13, we would add 5. If we try and find the second difference, we will notice that the second difference is positive 2. Therefore, using our prior knowledge, we know this will be a quadratic function. In number 2, if we use our rule from the previous lesson on how to algebraically always complete a square, we would use b divided by 2 squared. The b in this case is negative 6. So we would take negative 6 divided by 2 and square it to complete the square. We are asked in this case if this is a perfect square. So when we divide negative 6 by 2, we get negative 3 squared and we get 9. Therefore, we do know that this is definitely indeed a perfect square. Because this function is a perfect square, we can rewrite this as a quantity squared. That means that we can rewrite this as x minus 3 times the quantity squared. If we use what we noticed in the previous example, 3, 0 would be the vertex. If we're asked to graph this function, we could graph this function by starting at 3, 0 as our vertex. Our vertex is 3, 0. From lesson 2 of this unit, we saw that we can use the a value to help us graph other points on the parabola. we can always use the rule over 1 from the vertex and up 1 times a. We can then graph another point by going over 2 from the vertex and up 4a. For example, if I wanted to graph another point, a in this case is 1, therefore I would go up 1 times 1, which is 1. So I would go over 1 from the vertex and up 1. I know a parabola is symmetric, so I do know that the other point that I could plot would be 2, 1. If I wanted to plot another point from the vertex, I would go over to the right 2 and up 4 times 1, which is 4. So I would go over right 2 from the vertex and up 1, 2, 3, 4. Again, because I know a parabola is symmetric, I would go left 2 and up the same amount, 1, 2, 3, 4, to graph my parabola. If we examine a quadratic function where a is not 1, such as in number 7, we are asked to find the vertex again and graph it. When we complete the square, we must recall that the greatest common factor will need to be taken out of the expression 2x squared minus 12x. The GCF in this case is 2. When we divide by 2, we will get 2 times the quantity x squared minus 6x. Completing the square, negative 6 divided by 2 squared would be negative 3 squared, which is 9. So completing the square would give us a positive 9. If we are rewriting this equation in another way, we would keep the 2 on the outside and rewrite that as a perfect square. X minus 3 squared. In this case, though, we have 2 times 9, 2 times 9, or we have 18 little squares. According to the question, we only wanted to have 17 little squares. If we recall, when we complete the square, we will have to subtract 1 on the end as our k value in order to get from 18 squares to 17 squares. The vertex in this case is 3, negative 1. If I plot the vertex, 1, 2, 3, negative 1, I'm going to use the same rule as the last question to find my other 2 points. I'm going to go over to the right 1 and up 1 times my a value. In this case, my a value is 2. So I will need to go over 1 from the vertex and up 2. To plot my next point, I will go right 1 and up 2. Because a parabola is symmetric, I know that if I go left 1, I will also go up 2 to find another point. Likewise, I can go over 2 and up 4 times a, or 8. In this case, I would go right 2 and up 2, 4, 6, 8. It is symmetric, so I can do the same thing on the other side and graph my parabola. Recall that the axis of symmetry must go through the vertex of the parabola. Therefore, my axis of symmetry in this case is the equation x equals 3. We know our vertex is 3, negative 1, and 2 other points would be 4, 1, and 2, 1. Therefore, we have graphed the correct parabola. In summary, we can modify a quadratic equation in standard form and place it in vertex form by completing the square. The HK values will always be the vertex of the parabola. The A value of the function in the graph will help to tell us where our points are located, and it represents the vertical stretch or shrink of the function. We always move right 1 from the vertex and up 1 times a, over 2 from the vertex and up 4 times a, and so on. If you need more help on the Ready, Set, Go homework for this task, please check the Student Support site.